Hello guys, today I'm going to continue what we discussed last time, and we will continue to cover homogeneous and rotational transformations. Recall basically in robotics, usually when you have a robot with multiple links, each link will have its own frame. Like in this case, link 1 has frame 1 attached to it, so that frame 1 basically moves and rotates with link 1, it's like part of it. Link 2 has frame 2 and link 3 has frame 3. Ground also will have its own frame, which is basically a fixed frame. We said we have two types of transformations, rotational transformations and homogeneous transformations. If you look into that, so this is a homogeneous transformation. Part of the homogeneous transformation, so the first 3 rows and 3 columns is the actual rotation transformation. The last column is basically the offset or the coordinate of the center of the second frame with respect to the first frame. And here we have to put one in order for us to do both rotation and transformation simultaneously in the same homogeneous transformation. And also recall that the first vector, right, of a rotation transformation is, in the case of, for example, this T01, the first column is how do you basically express x1 in the previous frame or the preceding frame, right? So here x1, you're gonna do, if you project x1 on x0, you're gonna get cosine q1 or cosine theta 1, which we simplify here and then as a c1. And then the y component of vector x1 is sine theta 1. And then you look at y1. So the x component of y1, basically you have an angle theta between y1 and then y0. So your x component is going to be minus sine theta 1. And then the y component is going to be cosine theta 1. And the z1 in frame 0 is basically 0, 0, 1 because it is along z0. The third column basically is you are expressing the origin of that, or of frame 1 basically in frame 0. So if the length of link 1 is L1 as indicated here, then what would be, how can you represent the vector O1 in the base frame? So it is simply L1 cosine Q1, and in the x component, in the x direction, and then in the y direction is going to be L1 sine theta 1. All right, guys, so pretty straightforward. So you can write T01, and then in a similar manner, you can write T12. Basically, that would be the homogeneous transformation between frame 1 and then frame 2. Okay, so here you will use Q2, right? Q2, and then that Q angle basically has to go all the way to actually to this line, right? That it doesn't actually end at y1, it actually ends at x2. So Q2 locates vector x2 with respect to x1, all right? So angle Q2 is between x1 and x2 and not x1 and y1. If you do this, basically, you will also end up with the same thing, right? Here you have the cosine of, if you project x2 on x1, you're gonna get cosine Q2, and you know, if the angle is greater than 90 degrees, then your x component, right, or the x component of vector x2 with respect to x1 will be negative, right, as you would probably see on this figure very easily. Okay, so once you have all these homogeneous transformations, T01 is obviously the mapping between frame 0 and frame 1. T12 is the mapping between frame 1 and frame 2. T23 is the mapping between frame 2 and then frame 3. You can basically multiply all of these together, and then you can end up with T03, or you can get 202, etc. Okay? And recall, when you are using a homogeneous transformation, let's say if I have a vector that is expressed in frame 3, right? Let me actually do some annotations over here. So let's say you have a vector, right? Let's say I have that vector, and obviously that vector here is going to have some, you know, some component along x3, and then it has some component along y3. Okay, let's say you multiply T03 by that vector. Let's say this component here is 1, and then this guy here is 1.5, right? What happens if you multiply this vector by this homogeneous transformation? If you do so, basically you get that vector, right? So you get that vector, and then the x component of this vector, it's going to be, you know, you're going to map this guy all the way down, right? You're going to be basically finding this value right there, right? And then the y0 component, basically, you're going to be finding this value all the way from here to here. Okay, so this is a homogeneous transformation. Obviously, if you do a rotational transformation of this, right, it's like you are simply getting the projection of this vector into the x0, y0, z0 frame, right? You are looking at the projection of this, or the shadow, basically, of this vector into the baseline. Okay, and we've also mentioned this one last time, basically, the homogeneous transformation, again, is you have your rotational transformation initially, and then you have that offset vector. Remember here, you always have to put 1 and then a 1. If you actually made this guy 0, then you multiply 0 by the offset. So it's like you're only doing a rotational transformation, or essentially, basically, just doing vector projections between different frames. All right. So let's look into this generic rotations about x, y, z axes. Overall, we can actually write the rotation about the x-axis to be equal to this homogeneous transformation, right? And obviously, I'm putting the last 0. So I can also write the rotation transformation as a 4x4 matrix. So I can actually use it. So all of them, basically, rotation and translations can be a 4x4, and then later on I can use those as a sub blocks for me to be able to do, like, manipulation operations. So the rotation, so these are rotations. I will just explain rotation about the z-axis, right? What I mean by that, basically, is I have a base frame which is x0, y0, z0, right? And obviously, this has to be a right-hand rule, right? So x cross y is going to give you z0. Now, if I tell you, what if I rotate this frame about the axis about the z-axis by an angle theta, right? So now x1 was initially at x0, but now that has been rotated by theta. So this is your x1, and then that is your y1, right? If I want to actually write the rotation, remember the first column of my rotational transformation is what? Is x1 as viewed in frame in the base frame, right? So what is the x component of vector x1? It's cosine theta, right? So what would be the component or the projection of x1 on x0? It will be positive, right? Because it is along the positive x0 direction, so it's going to be cosine theta. How about the y component? It's going to be sine theta, right? Cosine theta, sine theta, and then 0, 0, right? Because it has no component along the z0 axis because it is an xy plane or x0, y0 plane. Now the y component, so y1 in frame 0, right? How can I express that unit vector y1 in the base frame? Obviously, it has a negative component along the x0, which is minus sine theta. So this is my sine theta minus sine theta. Along the y0, it will be cosine theta, and then 0 because it has no component along the z0 axis. And then lastly, you have 0, 0, 1. All right. Now regarding the translation matrix, basically, or translational transformation, I can literally write it like that. Basically, the same unit vectors, right? I'm not changing rotations or I'm not doing anything, but if I want to translate along the x direction, I would simply basically add d over here, right? If I want to translate along the y, I will simply basically add d. So I'm going to translate here along the y-axis by a value of d. So if you do this homogeneous transformation, it's like you moved your frame along the y-axis by a value d. All right, so now that we actually have all these transformations, so we have rotation about x, rotation about y, rotation about z, and then all of these are 4x4, right? This is also, all these again are 4x4. Now I can actually go and then put these in MATLAB, and then I can take advantage of the powerful libraries and symbolic computation capabilities of MATLAB to be able to do these array multiplications. So I can now define in MATLAB, I can define a function that does rotation. So the input to this function, which is a rotational transformation, is theta. So as soon as I give it theta, it will basically produces the rotation about the x-axis, right? Which is 1, 0, 0, 1, 0, 0 in this direction. And that's going to be cosine theta minus sine theta cosine theta. So A right now is a 4x4 matrix that basically defines rotation about the x-axis. Okay, so we can take a look at it again. So this is rotation about x, 1, 0, 0, 0 cosine theta, 0 minus sine theta cosine theta, which is 0 minus sine theta. Okay, so this is your rotation about the x-axis. in MATLAB, when you define a function, right, it will be on its own script, okay, and this will be the first line in MATLAB. For example, this is your function. This is a rotation about the x-axis, and now basically you can call this function whenever that you want. Okay. Then to be able to actually call that function, you will have to symbolically define your variable theta. So sims theta basically will define theta as a symbolic variable, and then rotation about x theta, basically it will basically simply output this array. Okay. And then in a similar manner, we can define rotation about y, and then rotation about z, and then rotation, and then the rest of the translations. Okay, what I'll do, you know how to input or how to add basically functions into your MATLAB. So now we can do like rotation about x, y, z. So you should save all these rotations and translations functions into your directory. So these will come very handy when you are doing your assignments, right? Okay, so let's say you have this problem. I don't think we did actually. Okay, so let's go over this problem. Basically, this is how many degrees of freedom this one is. You have 3 degrees of freedom, right? Theta 1, 2, and then 3. And you know, I would like to get the homogeneous transformation between the base frame and the last frame, right? Meaning that if essentially I have a vector expressed in the last frame, I can express it, right? Let's say I have a vector like that, right, expressed in that frame. I can basically find it with respect to the base frame, right? Okay, so what would be the rotational transformation between the base and then frame 1, right? The first component is going to be rotational transformation, so you have to express x1 in the base frame, y1 in the base frame, and you guys can imagine that you know, rotation r01, for example, right? Y1 is going to be 0, 0, 1, right? Because it's along the 0, right? How about x1? X1 is going to be along. So the x0 component of x1 is going to be minus sine theta, right? The y component is going to be cosine theta 1. And then the z is going to be, basically, it would be cosine theta 1, right? And then sine theta 1. So you rotate this frame by sine theta 1, then z1 is going to be pointing like that, right? And so you can quickly see that it's very simple. But I want to teach another way of actually doing that. So what you could do is you can basically follow the sequence of rotations that will actually lead you to basically make this frame be in the same direction as that frame. So how can I do that? So initially, so to be able for this frame to basically be in the same direction along this guy, right? Even including the angle theta 1. So you rotate the first frame about z. So now your x0 is pointing along x1, right? Now y0 is pointing toward the other direction. Then you rotate about x. So if you rotate about and this is a rotation about the current x-axis, right? So you rotate about z, so your x0 is pointed in that direction. Now you rotate about x. Now your x0 is along y, right? Okay, then you rotate about y by theta 1. Okay, so I'm gonna redo this one more time so it's all clear. So I'm gonna rotate about z by 90 degree. Now x0 is in that direction, and then y0 is toward the other direction, right? Now if I rotate about x by 90 degree, basically my y0, which was in that direction, now it's actually pointing along y1. So now actually I have the right orientation. Okay, so after the first two operations, basically my frame looks like the second frame. And now I still have theta 1, so I will rotate about the existing y-axis, right? So you rotate about y, which is already now up by theta 1, and then you translate about y by how much? By L1. So we're done with the first transformation. And remember, you have all these functions in MATLAB, so you can simply do this as an array multiplication in MATLAB or a matrix multiplication in MATLAB. Now let's look into the second one. What would be the sequence that would get me from frame 1 to frame 2? Obviously, so we are already in the same direction, so I will simply rotate about theta 2, right? So this frame is rotated about z1 by theta 2, so rotate about z by theta 2. Then you translate along x, right? Current x-axis by length L2, and then this is the same thing on the last one. So now you have H01, you have H12, right? And then you have H23. You can actually get H03 by doing that. And then this is what we have here, right? So in MATLAB, when you do a rotation about pi over 2, sometimes you end up with a very small value. So that's why I round it. Okay, so you can round that rotational transformation, so you don't end up with very small numbers that will ultimately gets multiplied, right? So in the array in MATLAB, if this number is 0.0001, right, it will actually assume it's a number, and then it will add it into the multiplication, and it will complicate stuff, for example. But what you should do is just round the rotation. Okay, so the first line is basically exactly what I have here, right? Rotation about z by 90. Right, rotation about z by pi over 2. So here I'm rounding this down to 2 significant figures. Then you rotate about x by pi over 2. Again, I'm rounding this to significant figures. There must be a way around this rounding, basically. I'm sure some of you guys will be able to figure it out. So here I just want to, like, when I rotate about pi over 2, so basically I'm going to have cosine pi over 2 and sine pi over 2. In my MATLAB, basically, like if I do sine pi over 2, I'm getting a very small number. I'm not getting a 0. Or I'm getting like a number to the power 10 to the minus 15, and it's being carried in the computation. But when I round it off to 2, it will be 0, so I'm good. Okay, second transformation is this, right? And then this is the third transformation. When you do this, right, H01 is minus sine theta cosine theta. So let's look into this component, right? Remember, the first column of your homogeneous transformation is x1 in frame 0, right? Or here x2 in frame 1. So x1 in frame 0, then you're looking at what is the x component of vector x1 in frame 0, what is the y component of vector x1 in frame 0. Okay, so let's look here. So if you rotate this guy, what would be the x component? It will be minus sine theta 1, right? Because after that, this frame is rotated by theta 1, okay? Then x1 is going to be slightly like that. Then its x component will be minus sine theta 1. Okay, maybe I can try and then illustrate that by drawing it, right? Let me pull up a line. So this is your frame here, right? So this is along x0, right? So this is simply the continuation of that. So after you rotate this guy, then x1 is going to be toward in that direction, right? Let me actually make it a vector. Okay, so this is my x1. So if I basically project this one after rotation theta 1, and this angle here is theta 1, then your x component mazboot is going to be how much? Minus sine theta 1, because it's pointing along the minus x0 direction. So this value from here to here, okay, this value, right? This value right there is equal to how much? Minus sine theta 1. How about along the y0 is cosine theta 1? This guy is cosine theta 1. Okay. Okay. How do we do this? Annotate, erase. Okay. Okay, so you see it's minus sine theta 1 and then cosine theta 1, right? So the x0 component is minus sine theta 1 and then y0 is cosine theta 1. Okay, and this applies to all of them. Sometimes it's not very easy. Just apply the homogeneous transformation, that will give that to you. And then when you do the H01, H02, H03, you will basically, so H02 is H01 times H12. Basically, it's associative, right? H03 is H01 times H12 times H03. So now that you actually have your homogeneous transformation, you can do the inversion, right? You can kind of express the vectors in both directions. Okay, you can do H03 is, in MATLAB, it will be the P inverse, right? The P inverse of that. Okay, and obviously one way would be to simplify it, right? When you simplify it, you will be able to see it nice and clearly, right? So this is our result here. This is my T02. I can simplify that. If I ask you for rotation transformation between frame 0 and then frame 2, you will simply cut that vector, right? You would look at the 3 and 3 component of that. Okay, and then this is T03, and that is it, guys, for what I want to cover in this lecture. Okay, what I encourage you guys to do is do whatever that I just did in MATLAB. So sit down and then program your MATLAB basically with these functions, right? Program all these, and then on your own, guys. Don't ask for anyone to help you, because this is very important for you to understand. Put it in a script and then obtain these homogeneous transformation and make sure that you are actually getting the right values. Okay, might be a good idea to not even look at that, just start from this problem and then try to work it on your own. Maybe use another rotation, maybe use another sequence, and then make sure that the sequence that you use basically will actually give you the right answer, because all this will lead you to the same answer. All right, guys, so that is it for this second lecture.